Let's go through the last of the quadratics lessons here. We're just going to review a lot of stuff working with zeros of a quadratic. So a lot of this you'll have seen last year. We're going to throw in some new stuff as well. Now, first thing that you might remember from last year is just talking about how number of different ways a parabola can intersect the x-axis. So you did see last year and this year that you can have parabolas like the one you can see here that has two x-intercepts. You can also have parabolas like here that have no x-intercepts. And you can have ones where the vertex is on the x-axis where you have one x-intercept. So those are all things you've seen before. So you know there's three different possible numbers of intercepts you can have, either 0, 1, or 2. So now that we know that's the case, can we express, we look at three main forms, standard form, factored form, and vertex form. Can we express each of these three cases, 0, 1, or 2 x-intercepts in each of these forms? Okay, so let's think about that for a sec. Let's take a look at factored form first. So you could probably pretty quickly write a factored form that has two zeros. You're going to have two distinct factors or brackets. So here's a perfect example right here. This one has x-intercepts at -7 and 5/2. If there's going to be 1, 0, what you often see is only one distinct factor. So for example, -3 times x plus 7, x plus 7. Now, often you wouldn't see it written this way. You'd see it written as -3 x plus 7 all squared, which in a way kind of looks like vertex form, but this is what is telling you that you only have one x-intercept, only one at x equals -7 in this case. Now, if there's no zeros, there actually is no way you can write a factored form, okay? Because in order to have zeros, you have to have distinct factors or brackets to get our x-intercepts from, and if we can't get the x-intercepts, then, well, we can't write factored form. So if you're looking at a case where there's no zeros, you can't have a factored form. Okay, looking at the case for vertex form, well, let's think about what a parabola looks like if it has two zeros. Okay, so in order for it to have two zeros, there are two possible situations. So if these are my axes right here, I can either have a parabola that, if it's opening down, is going to have the vertex above the x-axis, or if it's opening up, we'll have the vertex below the x-axis. These are the only two possibilities to have two x-intercepts. So let's think about what's happening here. So in the first case over here, the one on the left, since it's opening down, we're going to have an a value that's negative. So a will be less than 0. Okay, and our k value, so the value of the optimal value right here is positive above the x-axis, so k is going to be greater than 0. Okay, so that takes care of what a and k do in that equation. Now if you look at the other possibility over here, the one opening up, here our parabola is opening up, so a is positive, so a is greater than 0. And our k value is below the x-axis, so it's negative. So what you're seeing here in both of these cases is that the a and the k have different signs. So in this case, the a is negative and the k is positive. Here the a is positive and the k is negative. So that would be your criteria to having a parabola with two zeros in vertex form. And this isn't necessarily something you have to memorize. I mean, you could take a quick sketch of this. You could throw in your vertex at -5, -7, have it opening up, and you could see that there are two zeros right away. But in general, for this case, if there's two zeros, a and k will have different signs. Okay? If there's only going to be 1, 0, well, here we're looking at the situation that we saw with factored form again, where we have the vertex touching the x-axis. Okay, whether it's opening up or down, your vertex just touches there on the x-axis. So in both these situations, I mean, a could be positive or negative because it's opening up or down. What you'll notice here in both these cases that the k value, so the y value of the vertex, is 0 in both of these cases. So looking at vertex form right here, if you have k equals 0, well, that part goes away in the equation. You just have a bracket x minus h squared. Okay, so you'll get an equation that looks something like this. This is an example right here. So here the vertex would be at 2, 0. Okay, and last but not least, the case where we have no zeros. Well, looking at the two possible situations again, if we do little sketches here, for there to be no zeros, we could have a parabola that is opening up with the vertex above the x-axis, or a parabola that's opening down with the vertex below the x-axis. So let's compare the a and k values here. So here, opening down, a is negative, and k is below the x-axis, the optimal value, so that's also negative. Over here, opening up, a is positive, optimal value is above the x-axis, so k is positive as well. So in both of these cases, a and k have the same sign, either they're both positive or they're both negative. So here's an example of one right here. Okay, so in this case our vertex is at 7, negative 8, so somewhere down here in this quadrant, and we're opening down. Okay, last but not least, let's look at standard form. Okay, and with standard form, what's going to help is remember the quadratic formula. So if we were trying to find the zeros, and especially if we didn't factor, we'd have the y value equal to 0, and we'd have something that we'd have to solve. We'd use a quadratic formula in a lot of cases to solve for that. So what's going to determine the number of zeros we have is this part of the quadratic formula, the b squared minus 4ac, also known as the part that goes under the square root in the equation. That determines the number of zeros we have. So let's say, for example, if what's under the square root was negative, okay, then we'd have a negative number underneath the square root. Well, we can't take the square root of a negative number, so that would actually mean that this equation would be impossible to evaluate. So what's underneath the square root is negative, it's actually telling us that we have no zeros. So for there to be no zeros, we'd be looking at the case where the discriminant b squared minus 4ac is less than 0 or negative. Okay, and there's an example of one right here. So if you were to try the discriminant here, and if you're trying to find the zeros using quadratic formula, you'd have negative 2 squared minus 4 times negative 5 times negative 7. Okay, so this would give you 4, and that would give you minus 140. So it would be something negative. The actual value here doesn't matter that much. The fact that it's negative is what's important. Okay, so again, if you get negative in the square root in the quadratic formula from the b squared minus 4ac, we have no zeros. Okay, now let's just say what's underneath the square root here, the b squared minus 4ac was 0. Well, then you'd be left with, well, negative b plus or minus 0 over 2a. And we all know that adding or subtracting 0 doesn't change anything, so that plus or minus, which gives you the two solutions when you're solving the quadratic formula, wouldn't actually happen. You only get the two solutions. So if your discriminant is going to be 0, it means you have one x-intercept or 1, 0. Okay, and last but not least, the only remaining case is if the discriminant is positive, and that's the case that you see just about every single time you use quadratic formula to solve. You get two answers out of the quadratic formula. So again, here's one right here you can try. You can calculate the discriminant b squared minus 4ac, and you'll get a positive answer. Okay, so here's something like you to try now to putting this all together. There's 6 different equations here in a variety of different forms. I just want you to tell me how many zeros there are. You don't necessarily have to find the zeros, just tell me if there's 0, 1, or 2 x-intercepts for each of these cases. So take a minute or two, try this one on your own, and push play and you're ready to go through them together. Okay, so I guess I'll start with the factored form one here first. This one's probably easiest to look at. So right away, looking at this, we see 2 distinct brackets, 2 distinct factors. So from each one of these, we're going to get a different x-intercept. This one should have, therefore, 2 x-intercepts or 2 zeros. Next, I'm going to deal with the ones in vertex form, so b and e. So starting with b, vertex form is not too bad to find the number of zeros either, because you can do a quick sketch. Looking at this one here, we have a vertex at positive 4 over 5 and negative 3. Sorry, 4 over 5 and negative 3. Okay, so you make a quick little sketch of that on a graph, and I'll just do that really up here. So positive 4 over 5, negative 3 will be somewhere down this quadrant, the bottom right quadrant down here. And we can see from our a value here that we open down. So a very quick little sketch there tells me that, hey, this graph is not going to pass the x-axis at all, so I'm going to have no x-intercepts. Okay, I can do the same thing with e down here. Again, doing a quick little sketch, I can see with my vertex being at 11, 7, that's somewhere up in the top right quadrant. The a value is negative, so we open down. So I can see from my graph here, 1, 2 x-intercepts, so 2 zeros. Okay, so that takes care of the factored form and vertex form examples. Now, let's try and look at the standard form ones. So again, for standard form, you want to go and take a look at the discriminant. So for each of these, you're going to want to calculate b squared minus 4ac. So in this case, you're going to get negative 6 squared minus 4 times 3 times 3. Okay, and if you run that through your calculator, you're going to get 0. So discriminant of 0 tells us that we have 1 x-intercept. Okay, we'll repeat the exact same process down here for this guy. So for d, we're going to get, for b squared minus 4ac, b is negative 1, so we get negative 1 squared minus 4 times negative 3 times 17. So run that through your calculator and you should find that you get a positive answer. Okay, in fact it's actually equal to 205. But all that matters is that it's positive, so that tells us we have 2 x-intercepts. Okay, last one we're going to look at here is f. Now that's actually in partially factored form, so you have a few different options here. You could actually find the vertex, put it into vertex form, solve from there. You could put it into standard form, use discriminant, solve from there. Lots of different options. So just to remind yourself what partially factored form does. So from these two brackets here, you get x equals 4 and x equals 3. Now these are not the zeros. Okay, it's tempting to think those are the zeros because they come from brackets, but this plus 1 means we're not actually in factored form. What these are actually points. So it tells us that when x equals 4, y equals 1, and when x equals 3, y equals 1. Okay, so if we were to take a look at those on a graph, so we'd have a point at 3, 1, so somewhere there, and 4, 1, somewhere here. Okay, so that's all it's telling us right now. Now, we could probably look at the direction of opening here. If you actually look at it, there's an a value of 4 here. If you were to look at the a value in standard form, you'd have 4 times x times x. So that gives you 4x squared. A value is positive, so we're opening up. The only question is we don't know how far down our optimal value is, so we still need to actually find our vertex, or we can work from standard form. So what the approach you take is up to you. I'm going to put this into standard form because I like using the discriminant. So taking a second and putting this into an array. Okay, that's going to give me x squared minus 4x minus 3x plus 12. So expanding all this out, okay, I still have to do a bit of simplifying here just to make sure. So it gives me 4x squared minus 28x. And here I've got 4 times 12, which is 48, plus 1, which is 49. Okay, so from here, once I'm in standard form, again, I just want to find the number of zeros so I can look for the discriminant. So it gives me negative 28 squared minus 4 times 49, which you run through your calculator should give you 0. Okay, so once we know that's 0, that tells us that we should have 1 x-intercept. Okay, so a couple more examples to try here. So now we're being given part of a quadratic equation, 3x squared minus 5x. We don't know the last value, k. We want to make sure that we find a k value so that we have two different x-intercepts. So the approach to take here, we're in standard form. So if we're in standard form and we want 2 distinct x-intercepts, that's telling us that the discriminant, b squared minus 4ac, has to be positive. So we're going to apply that to the equation that we have already and see if we can find restrictions on our k value right here. So let's just set it up first. So if I'm taking my discriminant, I'm going to have negative 5 squared minus 4. My a value is 3. In this case, my c value is just k. And again, since I need to have 2 distinct zeros, this whole thing has to be greater than 0. So that's now the equation I have to solve. Now it is an inequality, but we've seen how to solve inequalities back at the start of the semester. So let's just simplify as much as we can first. So negative 5 squared is 25. 4 times 3 is 12, so I have 25 minus 12k is greater than 0. Okay, subtract 25 from both sides, get negative 12k is greater than negative 25. And I'm going to divide both sides of the equation by negative 12. Remember, when I divide both sides of the inequality by negative, it changes the direction of the signs. So this means now k is less than 25 over 12. So what this is telling me, any k value that I put into the equation here that is smaller than 25 over 12 will give me 2 different x-intercepts. Alright, we're going to continue this in the next video, but I'd like you to try B and C on your own in the meantime, and we'll see you over there to take them up.